Okay, so this is the paper. If you want to look for the details, you can look for the paper. We also have the archive version and the code. And you want a demo, you can click this link. So this paper is a joint work with main author Valentine, and then our supervisor Nicola Gillis, and I'm Anderson. So in this talk, I'm going to talk about single channel blind source separation. That means you only have one measurement, that is one sensor, and you have multiple sources. And I want to solve this problem for audio data source separation. That is, I'm considering audio data, not other data, although this framework works for other data, but less focus on audio data source separation. And here, blind means I don't know the number of sources, I don't know how they behave, I just have the data. So this is a quite restricted but standard data learning paradigm. Of course, then the question is how to do it. So, of course, as the title suggests, we will solve this blind source separation problem by using NMF with two twists. First is using Beta-Divergence. Second twist is we have something called minimum volume. If you are attended the doctoral school 2 days ago, I think you already heard of Jeremy's tutorial on what is NMF. In fact, he also mentioned what is Beta-Divergence a little bit, and also something called minimum volume. So in this talk will be exactly the elaboration from that point of view. So what is this model? Basically, it's an unsupervised learning model because we do it blindly. And we assume this data fulfill some theoretical condition. That means if the data fulfill some theoretical condition or assumption, then actually this model, we have theoretical identifiability guarantee. That means I don't care what is your data looks like, as long as they fulfill this assumption, then whenever you solve this model, you can find out the ground truth. That means the source that generate the data. This is actually very powerful. And then, of course, we propose an algorithm that solves it with theoretical convergence guarantee. And then, empirically, we also show that this model can solve the model order selection problem. That is, because this is a blind problem, that means we don't know number of sources. But in fact, our experiment shows that actually it's okay. We just pick a parameter R that denotes the number of sources to be very big. By solving this model, actually, if you use a wrong order, model order, it's okay. The solution will automatically cancel out those redundant components. I will show about this result later. The only drawback of this approach is just not fast. But this is recently improved in this paper. You can have a look. So, as I said, this also works for other applications. So what is the setup? I will jump very fast. So basically you have source, K source, capital K, and source, I denote it as S. And you are given a mix like this. And then you have the data, X. And then, of course, your goal is to find S from X. You don't know K and you don't know S. How do we deal with it? We run time frequency transform. You have X. After the time frequency transform, you have a matrix X. And then this is the complex matrix. We take the amplitude spectrogram. That means we take the amplitude, so we call it V. So basically, the framework is we work on V we decompose V using NMF. And there are some assumptions. I'm not going to talk about it. So this is the pipeline. You have an X, which is composed of some source. Then you apply a time frequency transform. A time frequency transform makes this X into a big X, that is a complex matrix. And then I take the amplitude, I call it V, and I run NMF. And then because NMF, I give you two factors, W and H. And then with W and H, each rank one factor, I consider it as a source under the assumption that each source making this X is well approximated by rank one factor. Well, it is possible this assumption is violated, but that will be some future work. And then with this real matrix, which is actually component amplitude spectrogram, we go back to the phase, and then we construct the complex value time frequency matrix, and then we do the inverse frequency transform. We get the signal Y1 to YR, and this will be the estimate of the source. And what is the model? Mean-value Beta-Divergence NMF. Very simple, it's just this model. So what does it mean? Basically, this is the data fitting term, which is beta divergence. Why beta divergence instead of for business norm? Well, very simple. For business norm, favor the large amplitude component. That means if you have some data and then some element are very big, then if you minimize the data fitting using F norm, then it will favor those large component. But if you use beta divergence, for example, like this, you can see that the expression tell you that it's invariant to the size. For example, if X and Y is very big, but you can see they divide each other, so the size cancel out. So that means this fitting term will also count the small component. And for audio data, because you know the music note, we have many things called overtones, and high overtones usually have small amplitude. So this means that we are also considering those small amplitude overtones. And this term is called log determinant volume. And this is actually a measure of how big is the volume of the convex hull generated by the column of W. And then these three conditions or constraints are just physical constraints. So we are not going to talk about how to solve this problem. If you are interested, you can look for the paper. So now we will jump directly to the theorem. That is, assuming we have the spectrogram V is decomposed as W star and H star, and we assume it's generally like this. And of course, we assume the rank is K, and then W is a non-negative, and H satisfy the conditions called sufficient scatter condition. In this case, if this is true, then if we minimize this model, which is basically this model without the log, then we will always get the W star and H star by solving this model. That means if we solve this minimization problem, we will always get back the ground truth if the ground truth really fulfill these assumptions. And here I'm saying that these assumptions are mild assumptions. That means W is non-negative because this audio frequency profile, which is always true. And then H is sufficiently scattered, means that in the audio node, there are some time point that certain nodes are dominant in that time period. That is, so this is in fact, to our knowledge, this is the first result of this kind of identifiability result in audio source separation. And then I'm not going to talk about the proof here. So if you are interested, you can go to this paper. So what is the algorithm? This is just a very high level description. You want to minimize this guy, and this guy actually looks very ugly because this is beta divergence, which is very ugly, and this guy is also very ugly, and you have some constraint. So the idea is to not minimize this guy directly, but to minimize this guy's upper bound. That means majorizer. So the idea is very simple. The beta divergence, we derive a majorizer, which is, let's say, call it function G. And then for this log determinant term, we also derive a majorizer, which is in fact the first order Taylor approximation of this function. Then, because this is a majorizer, meaning that this upper bound will always larger than F. So if we minimize this G, we are indirectly minimizing this F. So by doing that, because G is easier to minimize, so we can solve this problem. That is, we form an upper bound, we minimize the upper bound, then we update the upper bound and repeat. And it is just because this is indirect optimization of this problem that makes the whole algorithm slow. But at least we have some convergence guarantee. That is, we can show that the sequence W and H will converge to the locus minimum. And if the W and H that generate data fulfill this condition, then the local minimum will be the global minimum, that is this W star and H star that generate data. So this is the theoretical part. So here is a illustration. Let's say we have a simple music, and here you see we have a few notes. Mary had a little lamb. So this is the time series, and then this is the frequency transform. You get a time frequency matrix. This is the decomposition. From here, you can see that there are actually three nodes or three sources. That is the E node, the D node, and the C node. So you are expecting there should be three sources. R is 3, but here I'm running R equal to 7. That means I use a factorization rank much larger than the true data rank. And you can see that for the redundant component, you can see they are all 0. This is the frequency profile. This is the time activation. So you can see that this corresponds perfectly to the score, that is E node, D node, C node, D node, E node, E node, E node. So you can see this is Mary had a little lamb. And from here, you can see that the blue, no, the yellow, the green, and the red correspond to the three nodes. And actually, this model can also extract the onset of the node. You can see this component only consists of this kind of delta pulse. Actually, this corresponds to the onset of the node. And for component 3 and 7 are automatically set to 0. You can see from the activation, it's basically no activation. And same for here, for the frequency profile, you can see that these three actually are meaningful thing because they are musical notes. These are the frequency profile that have the overtone. And then for 3 is 0, 5 is 0. For 6, it does not look like a musical note, but this is actually the mechanical hammer noise of the piano. So that means this is legit decomposition. And then this is just to show that the decomposition fits the real data. That is the frequency, and the overtone fits the frequency peak of those music notes. And then this is what I just said. This can perform automatic order selection. Lastly, the previous example is just a simple toy example. Now this is a more complicated one. That first of all, it has more nodes. Number 1, that is more source. Number 2 is longer. This is just the first 2 measures of the prelude by J.S. Bach, and we have a real recording by some professional piano player. Actually, just use a music video collected from the YouTube, and then we run the algorithm to solve the mean beta NMF, and we get this result. So here, these are the note sequence in the score. As I said, this is blind source separation. So actually, we don't know the score, but then you can see from the decomposition, it fit perfectly to all the notes. This is just the first 2 measure of bars in the score, but for the whole score, it's the same. So in this sense, as I repeat, we solve a minimum volume beta NMF problem for single channel. That means you only have 1 measurement, less measurement than number of data source, and blind source separation. That means you don't know the factorization rank, and you don't have any prior information. And if the conditions are satisfied in the theorem, then the decomposition will be perfect because we have an identifiability theorem. And then for the algorithm, it always works because it's an MM algorithm with convergence guarantee. The only drawback is just a little bit slow. And then it's able to perform model order selection. That means even we don't know the R or the rank, but it's okay. You just make the R very big. Then finally, when you solve the problem, the R that is too big, those components will set to 0. So that's it. Thank you.
Thank you, Anderson. We have time for one quick question. Please raise your hand if you wish to ask it verbally or ask it in the chat. Don't use the Q&A board, please. Just use the, okay, I'll just read the question from Paul Magron here. The analysis of the factors W and H is nice, but how does this compare with a similar decomposition not using the minimum volume constraint?
Okay, if not, okay, the biggest difference is that If you don't use the minimum volume constraint, you don't have this guarantee. That means if you decompose the solution, it's possible you get good solution, but that's actually just by luck. But with this minimum volume, we will definitely sure this is not by luck, because it is the geometry that really fits the data. Because of time, I cannot show what is actually this guy is doing, but in fact, this guy is trying to quantify the volume that is the convex hull of the node. And if the nodes are distributed fulfilling this sufficiently scattered condition, then we are able to find this W and H exactly. I mean, up to round off numerical error. So this is a difference. And this is different from other methods that don't have mean volume, because for simple music, for example, this music, of course, you don't even need to solve it using NMF. I think you only need to solve it using simple PCA is enough. But what we are stressing is that with this volume for complicated music, for example, like this, with many notes, and also the music tone overlap, because you see here, this note will last for all this time period, which will overlap with all these notes under this condition, and also this is single channel. All this condition with the minimum volume, we can able to solve all those difficulty in this scenario, but which is not able for other methods that need prior information. So that's it.
Thank you again.